There we go. All right. Are we familiar with the term Bronsted-Lowry? We're starting to be familiar with those words. I would like you to tell your partner what is a Bronsted-Lowry acid. And what is a Bronsted-Lowry base. And if you don't have a neighbor, find someone to, Yonghyun, you could turn around and talk to Sion if you want to. Okay, what is a Bronsted-Lowry acid? It's a species that donates protons. So I'm going to make this the shortest definition ever. We're just going to call it a proton donor. Now, I'm going to put something in brackets here. When we talk about a proton in the context of acids and bases, what are we talking about? H plus. Are you guys okay with the concept that H plus is a proton? Okay, because it's just an H with its electron gone, and so all that's left is a proton. So what would that make a Bronsted-Lowry base? That would make it a proton, an H plus acceptor. There is another definition of acids and bases that you learned about. Do you remember what it was? Arrhenius. Arrhenius. And it is spelled Arrhenius. Arrhenius. So an Arrhenius acid, and what does an Arrhenius acid do? Tell your partner. So Arrhenius, and if you're on your phone, then I will say to you, you better have gotten like 100% on your last test and be expecting to get 100% on your next test. So Arrhenius releases H plus in solution. Okay? And that's how you can kind of remember is that Arrhenius releases H plus in solution. What does an Arrhenius base do? Yeah, it's a substance that releases OH minus ions. Okay, so I'm going to write a little formula of what happens when we put something into water, and you're going to tell me which of these four things it is according to what I have written. Okay? That's a Q. It's just a really bad looking Q. There we go. That's a bit better. So what do we have there? We have released hydroxide, therefore that is an Arrhenius base. Now I'm going to let you know, I'm going to get really tired of writing Bronsted-Lowry, so I'm going to start just writing BL, okay, because it's so long to write Bronsted-Lowry. Okay, let's try another one. Let's see. You tell me. Actually, yeah, I am actually asking about HNO3. I'm asking about HNO3 here. Otherwise, yes, you're right. There could be other answers. HNO3, what is HNO3? This is a Bronsted-Lowry acid because we are taking this hydrogen, yes, and we are moving it over onto the water. Okay, so now instead of having H2O, we have moved an H plus, so now we have H3O plus. Now I would like you to tell your partner what is the name of this ion here. This is the something or other ion. Now, I have a nice little hint for you. If you don't know what it is, it's actually written in your table of common ions. So if you want to take a look at your positive ions in your table of common ions, page 3 of your data booklet. Oh, wrong one. No, that's okay. Here we go. Look at that. So if you forget what it is, it's actually written here for you. It is the hydronium ion. Okay, so if you forget its name, it is right there for you. All right. So this is the hydronium ion. Is there any other type of acid or base in this equation? Tell your partner. Is there any other kind of acid or base in this equation? How about our friend water here? What's water acting as? It's acting as a base. What kind of base, eh? Bronsted-Lowry base, because it is a proton acceptor. It is taking that proton. Now, just for now, we're not going to worry about the products and what their roles are, because HNO3 is a specific type of acid. I'd like you to look in your data booklet on page 5. And if you don't have a data booklet, you're going to come and borrow one. Okay? Page 6. Sorry. Page 6 in your data booklet. And if you don't have one, you can come borrow one. Okay, they're just right here. Mm-hmm. Yeah. Okay. So go look up HNO3 and tell me what kind of an acid is HNO3. Oh my gosh, look, it's up in that gray area. And what's happening up in that gray area? These 6 acids right here, 1, 2, 3, 4, 5, 6, they are all strong acids. Okay, so nitric acid is a strong acid. And what I would like you to do is I would like you to tell your partner what a strong acid is and what a weak acid is. Whoops, wrong place. What is the difference between a strong acid and a weak acid? What does a strong acid do? It's an acid that dissociates how much? 100%, all of it, completely. Yes? So if I was to write H NO3. And I wanted to show what happens with it. What kind of an arrow would I have? I would have a one-way arrow. And I could show that dissociating into H plus aqueous plus NO3 minus aqueous. This is dissociation. Okay? Because it dissociates into the two ions. What kind of an acid are we talking about here? Is this Bronsted-Lowry or is this Arrhenius if we write the equation this way? This would be an Arrhenius. Because it releases H plus. But we have that one-way arrow, okay? Now, bopping back to what we had before, we have HNO3, still a strong acid, so we still have a, what kind of an arrow? One-way arrow, one way, because it is strong. But in this case, we have written it as a Bronsted-Lowry acid. Now, you may ask yourself, which one should I use? And quite frankly, you are allowed to use either. Yes? You can say, okay, I'm going to be simple and just be like, okay, I'm just dissociating it. I'm taking the H plus off and I'm taking the NO3 off and I'm just going to separate them. Here, whoa, did not want that. Here, if it says write the Bronsted-Lowry equation, then you would write this one. And you should be familiar with doing this. So I would say put it into your rotation, like maybe every second reaction, write it this way, just so that you feel comfortable with it. Yes? All right. So again, though, it's a one-way arrow. And this process is not called dissociation. This process is called ionization. Because we're not just splitting it apart, but we are turning it into ions. Now, am I going to get too worked up about the distinction, the difference between ionization and dissociation? No. Okay? But just so you know, there are differences between the words, but I'm not going to get too excited if you use the wrong one. If you say dissociation and you write this one right here, I'm going to be like, yeah, whatever, fine, you know. If you say this is ionization, well, it has turned into ions. So, you know, again, no big deal. Okay? Now, what if I asked you to define a strong Bronsted-Lowry acid? What do Bronsted-Lowry acids do? They donate their protons, okay? So it donates how many of its protons? 100% of its protons to a Bronsted-Lowry base. Okay? So that's where you would need to make the distinction. If it specifically says Bronsted-Lowry, please define a strong Bronsted-Lowry acid. You would say it this way. If you wanted to just define strong acid, you could just say it dissociates completely. Okay? All right, now what if we had NH3 plus water in equilibrium with NH4 plus and OH minus. I'm leaving some space underneath so we can write some stuff underneath there. Is it Arrhenius? Is it Bronsted-Lowry? Is it acid? Is it base? Now, first off, you should be able to tell me whether it's an acid or a base simply by looking at the products. What in the products tells you whether it's an acid or a base? You made hydroxide, therefore it must have been a base. Okay, so it's base. Is that an Arrhenius base or a Bronsted-Lowry base? Bronsted-Lowry base. Because who is it accepting a proton from? Who is giving the proton and who is accepting the proton? Water is giving the proton and NH3 is accepting the proton. So NH3 gains an extra H plus to become NH4 plus. And if you have water, if you have HOH, and if we take off an H plus, what are we left with? OH minus. Okay? Now, NH3, therefore, is the Bronsted-Lowry base. Bronsted-Lowry base. And water, what is water? Water is the Bronsted-Lowry acid. Yes, because it's accepting a proton. But this is a two-way reaction. You'll notice we've got two-way arrows. So is NH3 a strong base or a weak base? It's a weak base because we have a two-way arrow. So it is weak. Because it goes in both directions, you can also look at the products and you can say who in the products is the Bronsted-Lowry acid and who in the products is the Bronsted-Lowry base. So chat with your partner about that. Out of your two products, NH4 and OH minus, which one is the Bronsted-Lowry acid? Which one is the Bronsted-Lowry base? And if you're on your phone, you better have gotten 100% on your last test. Okay. Who is giving the proton in the products? NH4 plus is giving a proton to OH minus, and that makes NH4 plus the Bronsted-Lowry acid, and that makes OH minus the Bronsted-Lowry base. Excellent. Do you know what a conjugate acid base pair is? Tell your partner, what is a conjugate acid base pair? Let's start with the easy part of the definition. It is a pair of chemical, what's the word we use instead of things? Species. Which differ by one proton. Alrighty. Going back to our reaction, the NH3 plus H2O, could you please find two Bronsted-Lowry acid base pairs? Who are the pairs in that reaction? Who does NH3 go with? NH3 goes with NH4 plus because they differ by only one proton. So in a Bronsted-Lowry acid base reaction, a Bronsted-Lowry base turns into its conjugate acid. Okay? So here we have a Bronsted-Lowry base, turns into its conjugate acid. Who is our other Bronsted-Lowry pair? We have H2O and OH minus. Again, they differ by one H plus. Is good? Okay. So, will you ever have two Bronsted-Lowry acids on the same side of a reaction? Can you have two proton donors trying to donate protons to each other? No. You have to always have one acid and one base, and their conjugate partner will be on the other side of the reaction. Okay, let's go back to page 42. Where did I put it? Oh, it's here. There we go. So I've given you a list here at the top of the page of 3 Bronsted acids or Bronsted-Lowry acids. Could you please write their conjugate bases? Unless you've already written it, I should see you writing. We end up with Cl, right? Oh, Cl what? Cl minus. Where did that minus come from? Why do we have a minus? Because we lost an H plus. You have to make sure that you also lose that plus charge. Okay, so out comes the H plus. What is the conjugate base of HSO4 minus? SO4 2 minus and HPO4 2 minus? PO4 3 minus. Excellent. All right, now we've got some Bronsted bases and their conjugate acid. Please write the conjugate acids for these 4 bases. Who is the conjugate acid of CO3 2 minus? HCO3, and then the charge becomes just 1 minus. CH3COO, where do we put the extra H? At the end, okay? Yeah, I'm not going to get, like, if you were to write HCH3COO, that's not incorrect. It would be okay, but better would be CH3COOH. This is okay though, okay? HPO4 2 minus. Conjugate acid is H2PO4 minus, and HCO3, H2CO3 minus. No, it's not. It should be H2CO3 with nothing. Why will you not erase for me? Oh, because you're being silly. Okay, that's fine. Try you again. There we go. Okay. Do you notice any of these substances which appear on both sides? Look what we have here. We have HCO3 minus and we have HCO3 minus. It can be both a base and an acid. So we have HCO3 minus. Can you find another substance in our examples that can be both an acid and a base? Find another one in our examples. HPO4 minus, yes. Okay, so HPO4 minus, up here, it was an acid, and down here, it was a base. So we have HPO4 minus. So those can act as either an acid or a base. They can either donate or accept a proton. What do we call chemicals that can act as either an acid or a base. They are called, and you need to be able to write and spell this word, so try and write and spell it for yourself now, okay? And if you remember my little picture, do you remember my picture of the frog? Yes? What kind of animals are frogs? They're amphibians. And if you don't know that, that's not going to help you. But hopefully, a lot of you might know that they're amphibians. And that will give you the amphi. And they can either donate or accept a proton. Yes. So the frog can live in either, it can live in both the water and the land. So it is amphibious. These guys can both donate protons and accept protons, so they're amphi, and because they're accepting a proton, they're amphiprotic. So another definition of, write the word again, and say it out loud to yourself. Say it out loud so that you, like, it goes into your head. Okay, we're all going to say it together so you don't feel like self-conscious. Okay, I'm going to count down from 5 to 1, and then you're going to say amphiprotic, and we're going to say it 5 times. 5, 4, 3, 2, 1. I forget what number I'm on. Oh my God, I think we've done like 7 of them now. Okay, amphiprotic. Amphiprotic. And it is a substance which can act as both a proton donor and a proton acceptor. Amphi is from the Greek meaning on both sides. For example, amphibians can live on both land and water. So how will you know? Are you all done? How will you know that you have an amphiprotic substance? Well, if it's going to act as an acid, it has to have a hydrogen. Now, for almost all substances, we're on page 42 in our new book. Do you need the new book? Yeah. Almost all the time, you need a negative charge in order to be able to accept the positive hydrogen. Okay? Negative charge allows it to accept the positive hydrogen. Now, the exception to this is water. Water is amphiprotic even though it lacks a negative charge. But most of the time you'll say, I have a hydrogen and I have a negative charge, therefore it is, what's the word? Amphiprotic. Okay. And now we're just going to refamiliarize ourselves with this chart, okay? So we have this entire chart here. If you have a color printer, this document will be on like Teams, and you can print it out in full color. But what we've got here is we have, you'll notice, what do we have on the left side of the chart? On the left side, we have all the acids, and on the right side, we have all the bases. And what do you notice about all of these arrows in the gray section? They all go to completion. These are all one-way arrows. Okay? So they all go to completion. They all go 100%. So you end up with 0% of this and 100% of this. Okay? Now, when they dissociate, technically, who is the conjugate base of, say, HCl? Who is the conjugate base of HCl? Cl minus. However, what's going to happen if Cl minus tries to grab a proton? Nothing, because it is too weak to actually act as a base. So these guys up in the top part of the chart, too weak to act as bases. Okay? Now, I'd like you to think about this. We have a, what's a Ka, do you think? What do you think a Ka is? It's a KEQ for an, this is a Ka. What do you think A stands for? Acid. Okay, so let's look at writing a KEQ expression for, say, HCl. Ka for HCl. Ka is equal to, we've got our products, H plus and Cl minus. And our reactant is the HCl. Now, how much HCl do we have in solution? We've got 0, right? Yes? So whatever numbers those are, we're dividing by 0. So what's the only thing we can say about Ka? If you divide by 0, it's going to be very large. That's what we call it. We just call it very large, okay? There is no real meaningful Ka value for that, okay? Because there is no reactant. Now for the rest of the table, all the way down until we get to the little gray section at the bottom, all of these guys in here, these are all weak acids, okay? Now, there's no good way of saying this, so sadly, you know, you can see here we have our strength of acid over here, and which way is the arrow pointing for that strength of acid? It is pointing upward, where we have the strong acids at the top and we have the weak acids at the bottom. What do you notice about that arrow at the very bottom? The arrow stops. So down here, we have weak acids. Why are the hydroxide ion and the ammonia ion not weak acids? They don't qualify. Well, if we look at our arrows, what do the arrows do down here? They go only to the left. Yes? So really, these two rows are not here for hydroxide and ammonia. They are really here to say, if you have O2 minus, it's going to react 100% with water to give you OH minus. If you have, this line is not talking about ammonia, okay? It really isn't. It is talking about the NH2 minus ion. And what happens if you put NH2 minus in water? It goes 100%. It grabs all the protons it can, and it becomes NH3, 100%. Okay, so again, over here, we have 100% here and 0% here. So these guys on the left, they cannot give up their hydrogens. Hydroxide is never going to give up its hydrogen and become O2 minus. It's too weak to be an acid. These guys are not acids because they're too weak to be acids. Okay. And now we're going to dive into the middle of this table because the middle is actually where we spend most of our time. Whoa, what happened? Come back. No, where'd you go? 42. Here, there we go. Okay. Now it's a little bit awkward because you can hardly see it here, but up at the top of that middle section, you have these stronger weak acids, but they are still weak acids. And how do you know it's a weak acid? You know it's a weak acid because you have a two-way arrow. The weak acids all have two-way arrows. The weak bases also all have two-way arrows. Okay? And you'll notice the stronger weak acids, their conjugate bases are the weakest. The weakest weak acid, their conjugate bases are the strongest. So the stronger the acid, the weaker its conjugate base, and vice versa. Okay? And now we're going to just very briefly, because we've only got a few minutes left, we're going to start looking at predicting which side of an acid-base reaction is favored. Did you guys do this in Hebden at all? I can't remember. Yeah? Maybe no. Okay. So let's take a look at this reaction here. We have HCN plus F minus. This is on page 44. HCN plus F. Who are the products? Okay, there's only one proton. It's got to move from here onto here. So we're going to end up with HF plus, and who's left over? CN minus. I don't know why I wrote this twice. HF plus CN minus, which is favored in the reaction, the products or the reactants. Now, what we're going to do is we're going to decide who are the Bronsted-Lowry acids and who are the Bronsted-Lowry bases. So what I'd like you to do is I would like you to label each substance as a Bronsted-Lowry acid or as a Bronsted-Lowry base. HCN is a Bronsted-Lowry acid. F- is a Bronsted-Lowry base. HF is a Bronsted-Lowry acid. And CN- is a Bronsted-Lowry base. So now what you're going to do is you're going to compare HCN and HF. Okay, so you go to your data table and you say, I have HCN and I have HF. Here's HF. Here's HCN. Who is stronger? HF is the stronger acid. What have I done? Oh yeah, right. So this is the stronger, and this is the weaker. Now remind me, if the stronger the acid, the weaker its conjugate base, which means that F- is going to be the weaker. We can also look it up on the chart and confirm that. And the weaker the acid, the stronger its conjugate base. No, it doesn't really matter. But what you're going to find is that you'll always have the two stronger species on one side and the two weaker species on the other side, okay? The two stronger, always on one side. And you know what? You have no homework tonight. Unless you can think of something, because we're not ready to go anywhere yet. Okay, so if you didn't do any of the stuff over the break, oh, well, now would be your opportunity to get caught up on it, okay? Thank you. If you borrowed a data booklet, if you could bring it back. If you've lost your data booklet, I can get you another one. Okay. Yeah. Yeah, maybe next week then. No trouble. So good. I like working at like a very slow pace. It's my favorite thing. Like I got a lot done. I just did it nice and slow. Yeah. Yeah.
Like during the test because we had to write
No, no, you would not. No. Yes. Yeah, I just wanted to, because it wasn't like. So it wasn't awesome. So I'm just being so beautiful.
during the review I finished
Okay.
like most of
Okay.
I think it was like in the physics.
asking for clarification, okay? Like, don't hesitate to do that, okay? And certainly during flex time, come in, and ask about anything you don't. Okay? Yeah. Okay. You're welcome. Yeah. So we have our They stayed up all night studying for this one. Good job. Honestly, we've been studying for it. Personally, I would because I'm this student, like, however, these videos barely display the view. But good job. Actually, are you Hi. Yes. Let me find that for you. I just had, where did I put them? Did I pull them out? Where did I put them? Just let me go. Why am I so bad with paper? Okay, hang on. Not here. Not here. Yeah, it's probably in this pile somewhere. There we go. There we go.
Oh, can I do it now?
Yeah.
Oh, okay.
Is that okay?
Yeah, sure. I can also just like it for you. This is a bookmark, and that means like good luck.
Oh,
good luck
so
or
cute.
lucky.
Oh.
Yes.
I feel very lucky now. All right. So there we go. And let's grab.
Miss Spence. Oh, I was just wondering.
Oh, let's say yes. We're not also, because quite frankly, the straight geometry exam requires you to know our Okay, just letting you know. Yeah. Sorry. I don't think Okay. Oh. Okay, my friends, we have your test and art. Would you like them back?
Yeah, please.
Okay.
Well, I don't know. I just keep going. Like,
Okay, you're gonna get your test back. The bubble sheet is tucked inside. When you're done with it, you're gonna put back inside and then put it here. Yes? What are you going to do with the bubble sheet when you're done looking at your test? Put it back inside, and where are you going to put your test? Especially those people who just came in. What are you going to do with your test when you're done looking at it? You're going to hand it in, okay? But in the meantime, while you've got it, please feel free to ask me any questions, you know, if I've added it wrong or if you just didn't understand something, whatever. All right, so listen for your name, Ryan. Dorsa. Hannah. Daniel not here.
Thank you very much.
Isaiah. Sarah. Ellie. Cocolin. Shauna. Jessica. Jenya. Kaya. And you got like really pissed off? No. Jonathan. Samira. No Samira. Grace. Minnie. No Minnie. Ethan. No Ethan. Juan. Other one. No, other one. Jody. Kylie. Juan. Other one. There you go. Aaron. There you go.
Because I changed the Bro, that's